Hello everybody and welcome to video number 12. I hope you all had a pleasant weekend, and as always, if you have any questions about anything that we talk about today, please email me or give me a call or write it down and bring questions with you next Friday and be happy to answer them there. Um, let's get going over the homework we had. We got into chapter 6. Chapter 6 is about lines and planes in space. So we're going to be doing things that are a little bit more three-dimensional now, which I told you the hardest part with these kind of problems is if you're ever asked to draw anything, it's really hard to draw 3 dimensions on a flat surface. And I told you what we're going to do is if we want to represent a plane on a flat surface, we're going to draw a parallelogram, and generally we name a plane with a lowercase letter, M, N, whatever. So here I've got plane M, and I can't draw it infinitely long or high, so I only use this parallelogram to represent this plane. But remember, it goes infinitely that way and this way, and if you have a line L that goes through the plane. So this line L does not lie on plane M. It crosses plane M at this point. We'll call it point P. And we said that the point where a line crosses a plane, if a line intersects a plane, that means it touches it only once. And that point is called the foot. Also, with a plane surface and a line, only 3 things can occur. The line crosses the plane at one and only one point. It intersects the plane at the foot. The entire line L lies on the plane. So if I had a second line here, call it this way. Call that line M, or since I've already used M, let's call this line T. Line T lies on plane M. That means every point on line T is on plane M. And the third thing that could occur is a line never, if extended infinitely, if it never touches the plane or crosses the plane, it's said to be parallel to the plane. And again, like if you, your floor hopefully is a plane surface, it's level, and if you held your arm out so that your arm was parallel to the floor, it will never, no matter how far out you go, right or left. If you extend a line infinitely, and it never touches or crosses the plane of the floor, it is said to be parallel to the floor. So again, a line and a plane can intersect at one point called the foot. The line lies in or on the plane. You'll hear both words used. That means every point on the line. This line T lies on plane M. Therefore, every point on line T is on plane M. Or if you have a line that never crosses the plane, it is said to be parallel to the plane. Okay, and we are only going to talk about plane surfaces that are perfectly flat. We are not going to ever have a plane surface that has an arch in it. It's always perfectly flat. It has 2 dimensions, infinite length and infinite width. Okay, and you had homework on page 273. 272, 273, 274, and the first one, problem number 2. And luckily they drew it for you. You didn't have to draw it, so it was drawn for you. And they gave you that figure where you had 2 planes, S and T, and the 2 planes intersected. The planes were R and S. Plane R and S. And the first question said, where does R intersect S? And I said, if a plane intersects another plane, the points of intersection will always form a straight line. So part number 2A, R intersect S, it intersects on line AB, or whatever you want to call it. There are 3 letters they give you, A, D, and B. The line of intersection is either AD, AB, DB, or ADB, if you want to call it that. You can name it any way you want. Just put the little double-ended arrow on top of whatever 2 letters you use. So 2A is line AB. B. Where does AB, line AB, intersect plane S? Line AB, where does line AB intersect plane S? Now again, what that means is what points are in common with both the plane and the line, and your answer is, again, line AB. Every point on line AB is both on line AB and on the plane. So the answer to 2B is also line AB. Again, intersection means common to both. Every point on line AB is on plane S, therefore line AB is the intersection. Name 4 non-coplanar points. Name 4 non-coplanar points. There's a whole bunch of different ways you could do this. You could go A, D, E, and C. You could go C, B, E, and A. You could go B, D, E, and T. There are a whole bunch of different ways you could name it. Pick any 4 points that do not lie on the same plane. Non-coplanar. What points do plane A, B, and E determine? Well, there's only one plane in that figure that has points A, B, and E all on it, and that is plane S. So those points determine plane S. And remember, you had 4 ways to determine a plane. 3 non-collinear points. Those 3 points are non-collinear, and they form plane S. 2 intersecting straight lines always determine a plane. A line and a point not on the line determine a plane. And any 2 parallel lines determine a plane, because the definition of parallel were 2 coplanar lines that never intersect. So if you have two lines like this, they have to be coplanar. That means they form a plane. You can never have this way, remember, skew lines. Skew lines are not coplanar. F. What plane do line AB and ED determine? AB and ED. They intersect, and they both lie on plane S, so they determine plane S. Now, the word determine means what plane do they form? And again, any 2 intersecting lines, rays, segments, or any combination will always form a unique plane. And again, in that figure, lines A, B, and ED determine plane S. Name the foot of TC, line TC, in plane S. Well, if you notice, line TC crosses plane S at point E. Therefore, the foot of line TC on plane S is point E. Name the foot of TC in plane R. The foot of line of TC on R is point C. Line TC intersects plane R at point C. So C is the foot. Do CD and ED determine a plane? And the answer is yes. And the reason is CD and DE are intersecting lines. Even though the plane is not actually drawn in that figure, any 3 non-collinear points determine a plane. And those are 3 non-collinear points. And actually, if you look in the figure, there's that little triangle CDE, and I mentioned the other day, a triangle is always a plane figure. A triangle is 3 non-collinear points connected, therefore it forms a plane. And that little triangle, if you were to extend it out infinitely length and width-wise, you would have the plane determined by those 3 points, C, D, and E. So the answer is, even though it's not drawn there, yes, a plane is determined by those 3 points. And then if CD is perpendicular to AB, name the right angles. Now again, this is not drawn to scale, But if they were in fact perpendicular, what angles would you have? You would have angle ADC and angle BDC as right angles. If CD was perpendicular to AB, name the right angles formed. If CD is perpendicular to AB, you've got CDB and CDA as the two right angles. Okay? Hopefully everybody understands that one. Number 3, it said consider 2 points on a cylindrical surface. Hopefully you know what a cylinder is. It's like a tin can. So if I had a tin can, that's a cylinder. And it said, suppose you have 2 points on a cylindrical surface, such as the curved surface of a tin can. Does the line connecting the 2 points always lie on the surface? And the answer is no. You can have a point here. It's hard to show you again in 2 dimensions. It would be easier. Oh, watch this. Here, I have a cylinder. If I have a point here and a point over here, when I connect those 2 points, the line is not going to go around the cylinder. It's going to go from this point through the cylinder. So from the top, it would go from this point over to that point. It would go through the cylinder. It would go this way. It's possible if you had 2 points such as these two, I could connect them right here and right here, point A and B. Now when I connect them, the line segment is on the cylinder, but it doesn't have to be. If your point is here and over here somewhere, when you connect them, the line would go through the interior. It would go like this way. If I had this on the front side and that on the back side, when I draw this, again, it's hard to see in 2 dimensions. But that line would go through the cylinder this way, from point A to point B over here, and then continue on. Okay? Again, it's hard to see it 2-dimensionally. It's hard to see on a flat surface what's happening. So number 3, it said, does it ever lie on the surface? It could if you did it this way. The 2 points connected, this line does in fact lie on the whole cylinder, but it doesn't have to. Number 5, a 3-legged stool will never rock, even if the legs are different lengths. Many 4-legged stools wobble. And why is that? This is a case for making all chairs and all stools always have three legs as opposed to 4. When you have if you have 3 legs, you have at the ends of the legs you have a point, and those form 3 non-collinear points always form a plane surface. So if you have a 3-legged stool, it doesn't matter how the legs are. They could all 3 be the same length. You could have one shorter than the other. It doesn't matter. They will always lie flat because they form a plane surface. That's why a tripod for camera is 3 legs. Because no matter what type of surface you're on, and they're movable, you can change their length. So if you're on a slanted surface, you can still make a tripod stand perfectly straight. You readjust the legs and you form a plane surface that will allow you to have that tripod. Again, if you put a tripod on a curved surface, you would shorten up one leg maybe, and it would still sit perfectly flat even though it's on an angle, because 3 points determine a plane, 4 points do not necessarily. That's why if you sit on a chair, a lot of time your chair rocks. That's because all 4 legs aren't exactly the same length. Tables, a lot of 4, especially in restaurants, if you have four legs on a table and the table rocks, at the bottom of every leg they have these little adjuster screws, and if you turn, it lowers a pinion that goes down, and you can make the table steady. If you had three legs on a table, it would never rock. It would always, the three legs would always form a perfectly flat surface because three non-collinear points determine a plane. That's number 5. Number 7, I will come back to the proof. Let's go to number 13. Number 13 said if 2 points in space are equidistant from the endpoints of a segment, will the line joining them be the perpendicular bisector of the segment, and explain? And the answer is not necessarily. It could be, but it doesn't have to be, because of the following. On a flat surface in 2 dimensions, all right, if I had these 2 points P and Q, it said if I have 2 points, each equidistant from the endpoints of this segment. So if I had a point here, A, so that and that are equal, and a point B, say down here, so that this and this are equal, we had a theorem that said if that's the case and you connect A and B, you form the perpendicular bisector of the segment. That was the perpendicular bisector theorem. If you connect 2 points both equidistant from the endpoints of the same segment, you form the perpendicular bisector of the segment. But this said in space. Again, this one's hard to see, but so here I've got a plane M, and here I have a line segment A and a line segment AB. These 2 points lie on plane M. This question said if I have 2 points both equidistant from A and B, when I connect them, do they form the perpendicular bisector of AB? And the answer is not necessarily. If the 2 points lie on plane M, that will always be the case. But what happens if 1 point is here and 1 point is here, out in space? This point can be the same distance from A and B. This point can be the same distance from A and B. But when I connect my 2 fists, I get a line that doesn't even cross the plane M. So the answer to this question, again, is not necessarily. It depends on how you draw it. If all 4 points are coplanar, that would be the case, but the 4 points don't have to be coplanar. Therefore, when you connect the 2 points that they're talking about that are equidistant from A and B, the line segment or the line formed may or may not ever cross AB. You may get again, if you have your 2 points out here, when I connect my 2 fists, I get a line this way, which is never going to cross the plane M. So the answer, again, not necessarily. And then I also asked you to do problem 15. Problem number 15 said, the figure at right is a square pyramid. How many planes are determined by its vertices? We're going to do a lot of work in later classes with pyramids, but this particular pyramid is a 3-dimensional figure. So I've got A, B, C, we'll call that point back there D, and point E. All right. Now the bottom is a square, and a square is in this case lies on, it forms the base of this pyramid. So these 4 points right here have to be coplanar. So there's one plane, A, B, C, D. Okay, and then I've also got the 4, these are called faces, A, B, E, B, C, E, back face, C, D, E, and this other back left face, A, D, E. Those are triangular faces, and each of those triangles form a plane surface because they're 3 non-collinear points. So I've got A, B, E, That's a plane. I've got BCE, that's a plane. I've got CDE, that's a plane. Um, A, B, C, C, D, E, and the back plane ADE. Now, I'm assuming a lot of you stopped at that. That's understandable. That's a common mistake. But again, we said any three non-collinear points determine a plane. So here are 5, and there are 2 more. The 2 more are A, C, and E. Even though it's not drawn in there, it doesn't matter. Points A, C, and E are not collinear. Therefore, A, C, E would form a plane. Likewise, D, B, and E are 3 non-collinear points. Therefore, they are going to form a plane. So D, B, and E, there are your 7 planes. There are actually 7 planes formed by those 5 points. The bottom, the square base, those are all on the same plane. They form the base of this pyramid. And then each of the triangular faces form a plane surface because they're 3 non-collinear points, 1, 2, 3, 4. And then the 2 that aren't drawn in there. Draw a diagonal. The diagonal along with this point up here, it's called the vertex. The vertex of a pyramid is where all the triangular faces meet. And again, we'll spend a whole chapter talking about this later. But these 4 triangular faces, BCE, or the ABE, BCE, CDE, and ADE, form plane surfaces, 3 non-collinear points. And then you've got the 2 diagonals, AC along with the vertex, E, and DB along with the vertex, DBE forms a plane surface. So the answer to number 15 is 7. There are 7. Okay? All right, coming back and doing the proof. You were given this figure A, P, B, C. And you were told that you were given that CP is perpendicular to AP. You were given that CP is also perpendicular to PB. And you were given PA and PB congruent. And you were asked to prove that CA is congruent to CB. Prove that CA is congruent to CB. We actually did this problem as a, if you look on page 272, the practice problem is essentially this exact same proof. I'm going to call that angle 1 and angle 2. All right, so 1 given. All that info that we were given is now entered into proof. This is one way to do it. You can rearrange these statements, but I'm going to do this. CP is congruent to CP. Reflexive. Statement 3. Angle 1 and angle 2 are right angles. Definition of perpendicular. You were told that they're perpendicular. CP was perpendicular to PA. CP was perpendicular to PB. Therefore, 1 and 2 are right angles. The definition of perpendicular is if lines are perpendicular, they intersect at right angles. And I can then say angle 1 is congruent to angle 2. I told you I would accept this, and if you did this in one step, I would accept that. Right angles congruent. These triangles are now congruent. Side angle side, side angle side. So I've got triangle CPA congruent to triangle CPB. SAS, and I now can make my conclusion that CA and CB are congruent, they are corresponding parts. So CA is congruent to CB, CPCTC. Corresponding parts of congruent triangles are congruent. Sorry for the sloppiness. Okay? Hopefully everybody understands all those. Again, if there are any questions on any of the problems that we did, please ask on Friday, or if you can't wait till Friday, give me a call or shoot me an email. Okay, and that was it. And again, the really difficult part of this chapter is 3 dimensions. Trying to draw and express 3-dimensional figures on a 2-dimensional surface is difficult. And if you're asked to draw some things, you're going to find that it's going to be difficult. At least it is for me. You may be better at it than I am. Hopefully you are. Okay? Again, any questions, just write them down, bring them on Friday, or shoot me an email, give me a call. And I don't want to introduce a whole lot of new information today, but there is something. We're going to talk about a line and a plane being perpendicular. And they start off with a definition. A line is said to be perpendicular to a plane if it is perpendicular to every line on the plane that goes through the foot. That's a definition, so we don't have to prove it. So if I had a plane surface M, and I had a line L, and I told you L is perpendicular to plane M. By definition, what that means is any line I draw on plane M, and we'll call the foot, point P is where the line L intersects the plane. That means if I draw any line, T, or if I drew a line this way, it doesn't matter. Any line that I draw on plane M that goes through the foot, line L is perpendicular to all those lines, but they must go through the foot. There are an infinite number of lines I could draw on plane M that don't even touch line L. You can draw an infinite number of lines that do not go through point P. But if a line is on plane M and it goes through point P, which is where line L intersected the plane, it's the foot, then all of those lines are perpendicular to L by definition. A line is perpendicular to a plane if it is perpendicular to all lines in the plane through the foot. It must go through that point P. So there are an infinite number of lines I could draw on that lie on plane M that are not perpendicular to L. But if they go through point P, all those lines are perpendicular. Okay? And an offshoot of this theorem is the following. If I ever draw 2 intersecting lines, 2 intersecting lines determine a plane. That was one of the 4 ways we had of determining a plane, which means these 2 intersecting lines will say form this unique plane M. This theorem says if a line is perpendicular to 2 intersecting lines at their point of intersection, so if I have this line L and it's perpendicular to these 2 lines, so that's a right angle and that's a right angle, then it's perpendicular to the plane formed by the 2 lines. And we're going to call, if you ever use this, just go perpendicular plane theorem. perpendicular plane theorem. If a line is perpendicular to two intersecting lines at their point of intersection, it is perpendicular to the entire plane formed by the two intersecting lines, the original two intersecting lines. And again, think about it, it makes sense. Any two intersecting lines form a plane. If line L is perpendicular to both of these, it's perpendicular to the whole plane. That means any other line now that I draw in this plane, which I named M, that goes through that point, they're going to be perpendicular too, because of the definition. If a line is perpendicular to a plane, then it is perpendicular to all lines in the plane through the foot. And again, the hardest part here is visualizing everything that's going on, because we're drawing three-dimensional figures on a flat surface, on a two-dimensional surface, which makes it tough. All right, here's the way that we're going to use this. You're going to get a couple of proofs for homework tonight, but here you're also going to get some numerical problems, and here is a numerical one. All right, here's a plane M, and I've got all right, if I told you that AB is perpendicular to BD, if AB is perpendicular to BD, and the measure of angle ABD is 2/3 x plus 56. And the measure of ABC is equal to 2x minus 10. Well, right now I don't know what the measure of angle ABC is. I do know that the measure of angle ABD is 90, because they told you that the AB was perpendicular to BD. The only way AB is perpendicular to BC is if AB is perpendicular to plane M, then it's perpendicular to all lines on the plane through the foot. Okay? But I'm going to use this one. Since I was told that this is a right angle, or they were perpendicular, therefore it is a right angle, I can take that value, 2/3 x plus 56, and set it equal to 90. So you get 2/3 x is equal to 34. Multiply by 3/2, and you get x is equal to 17 times 3, which is 51. Hopefully everybody followed that. So x is 51, which now means that angle ABC is 2 times 51 minus 10. Well, 2 times 51 is 102. 102 minus 10 is 92. Well, if this angle is 92 degrees, that's not a right angle. Therefore, the question was at the end, is AB perpendicular to plane M? And the answer, or I'm sorry, I didn't even write that down, is AB perpendicular to M. In order for a line to be perpendicular to a plane, it has to be perpendicular to every line in the plane through the foot. Well, they told you that ABD is a 90-degree angle. ABC, working it out, is not a 90-degree angle. Therefore, AB is not perpendicular to plane M because it is not perpendicular to all lines in the plane through the foot. It's perpendicular BD, but it's not perpendicular to CB. And again, in terms of drawing it, what it means is if you were to have a flat surface, like the top of this desk here, and I've got a line on the flat surface, I can't have a line that comes in at an oblique angle. Remember, oblique is something not 90. And it would be perpendicular to a line on the plane, but it's not perpendicular to the plane itself. Again, if I like this edge right here, consider that a line on the plane surface of this bureau. I could have a line come down perfectly perpendicular to it, but I can tilt it. I could have this line coming out this way. Again, hard to visualize. Be easier if I was in person. But this line and the edge are, this might be a right angle, but this pen is not perpendicular to the top of this bureau. It's at an oblique angle to it, okay? Sideways. I could have a line this way, and this comes in like this. It's perpendicular to my arm. My arm might lie on the top, but this thing is oblique to the top of the table. So just because ABD is a right angle, it doesn't mean that AB is perpendicular to the plane M. And again, we did it numerically. I knew for a fact this was a right angle, set it equal to 90 and solve. You get X is 51, plug it in the other one, and the other angle is, angle ABC is not 90, it's 92. It's close, but no banana. Therefore, it is not perpendicular. AB is not perpendicular to plane M, so your answer is no. Okay? And I don't want to talk about anything else. So I'm just going to give you an assignment, and I'll see you on Friday. And the assignment is on page 278. One, 4, 5, 6, and 9. There are a couple of proofs in there, and we will continue to have proofs probably through the second semester until we get into the second semester, and then they will still follow us, but there won't be as many. We'll get more numerical problems. Okay? I look forward to seeing everybody on Friday. Thanks for your attention. Bye.